Let's get started. Hello, welcome to our monthly Science Connects webinar. My name is Connie Denise. I'm the Director of Donor and Alumni Relations at the Faculty of Science. We acknowledge that the University of Alberta is located on Treaty 6 territories, and it respects the histories, languages, and cultures of First Nations, Métis, Inuit, and all First Peoples of Canada, whose presence continues to enrich our vibrant community. The presentation today, The Science of Rock, Paper, Scissors, is about 30 minutes in length, followed by a question period. We will be collecting questions throughout the presentation. Please type your questions into the Q&A box, which will appear at the top or bottom of your screen. At the end of the presentation, these questions will be shared with the presenter to address. A video box of the presenter will appear. If it happens to obscure the presentation material, you can move it by clicking it and dragging it to another area of your screen. It is now my pleasure to introduce Martina Kalkunis-Ruppel, Dean of the Faculty of Science.
Thank you, Connie, and thanks to everyone for joining us for this month's Science Connects webinar. It's always such an exciting time for me to connect with you this way, and I love having the opportunity to connect with you. It's a different way of connecting, but it's one that I'm really enjoying. Thanks to everyone who continues to reach out to me, to connect with us through this series and to provide us with feedback. So I want to give just a couple of updates. Last week, we shared our Alumni and Friends newsletter as another way to stay engaged. And I had a short video message in that newsletter. And we're going to plan on sharing that quarterly in the future. So stay tuned for the September issue in your inboxes. This inaugural issue, we did a few updates. We shared our 2019 Donor Impact Report, and I want to take this opportunity to express my heartfelt gratitude for all of our donors whose critical support makes so much of what we do in the Faculty of Science possible. So thank you. I also shared that the next edition of our Contours magazine will also come out in September, so wait for that. We have an opening of our virtual summer camps coming at the end of this month on July 29th, and those are summer camps for K through 12 students. And another update is that we have appointed a new Associate Dean in the Faculty of Science, Dr. Tara McGee, who's going to especially be focused on equity, diversity, and inclusion issues in the faculty, and also engagement. So I welcome Tara, and I'm looking forward to working with her and many in the Faculty of Science community to address some of these issues that really are about community building in the Faculty of Science. So those are some updates. It's now my pleasure to introduce our speaker today, Ben Dyson. Ben Dyson is an associate professor in the Department of Psychology at the University of Alberta. He completed his thesis on auditory cognition at York University in the United Kingdom and went on to a postdoctoral fellowship at the Rotman Research Institute. He's held academic positions at the University of Sussex in the United Kingdom and at Ryerson University. His research explores cognition and decision-making in games, art, sound, and vision. Today, he'll share what we can learn about decision-making from simple games. So please join me in welcoming Ben, and we're looking very forward to this.
Hi everyone, so thanks a lot for the Faculty of Science for hosting this event, and I want to welcome all participants, particularly on this especially sunny afternoon that we have here in Edmonton. So today what I'd like to discuss with you is some research that we do in the lab here at Alberta, that focuses on the use of rock, paper, scissors as a game with which we start to understand a little bit about what humans do when they try to make decisions. So even though we'll be talking quite a lot about rock, paper, scissors, we'll be trying to open that out and expand that a little bit into thinking about what simple games can tell us about the way humans might make more complex decisions. So to start with, as with a lot of things in life, we can refer to an episode of The Simpsons. Now, some of you may be aware that a game of rock, paper, scissors was played on an episode of The Simpsons. And the representation of this game was actually quite accurate and also quite interesting in telling us a few key aspects of the game. So the narrative within the episode goes something like this. Lisa thinks what item Bart is probably going to pick. So Lisa thinks that Bart's going to pick rock, and meanwhile Bart's brain is also thinking about what item to pick, but not necessarily thinking about it from the perspective of Lisa. So Bart has a bias in his thinking and thinks, for reasons that may best go unexplored, that rock is unbeatable in the game of rock, paper, scissors. So Bart chooses rock, Lisa inevitably chooses paper, and Bart loses and Lisa wins. So this is actually instructive for two reasons. What it does is it reveals to us that even though we have three responses available to us in the game, we might not necessarily pick each of those three responses equally, and also that sometimes success in the game requires you adopting a theory of mind about the other player, what the other player might do, what the other player did in the past, and how that might impact on current performance. So even though we're talking about rock, paper, scissors, we're actually talking about a certain class of competitive environments here. And we describe these as zero-sum games. So zero-sum games are the case where if one individual has to win, then the other individual has to lose. And so in thinking about the data that we'll be talking about today, we might want to think about other contexts in which there are zero-sum games in kind of more playful or more serious aspects of life. So we might think about professional tennis, for example, where the outcome in a match has to be the case that one person wins and another person loses. If we wanted to think about a more serious domain, then we might think about counties or provinces or countries that in terms of their political stance. A country or district or province cannot be red and blue at the same time. The red political party has to win and the blue political party has to lose, or vice versa. So these are at least two examples of zero-sum games. So what we want to think about is how people use outcomes in order to determine future behavior. So to do this, we can think back to some really core evolutionary principles that are referred to often interchangeably as operant conditioning or reinforcement learning principles. So a lot of you, unfortunately, will be familiar with both punishment and reinforcement. So we can all probably generate examples where we've been reinforced for certain kinds of behavior. And when we're reinforced for behavior, this has an impact on future behavior. And we would describe this very generally as a win-stay mechanism. So if we've received a positive outcome for a certain kind of behavior, we're more likely to repeat it in the future. And a possible inverse of that is when we receive punishment. So for example, if we receive an explicitly negative outcome, we lose, we're more likely to shift our behavior. We're less likely to repeat behavior and more likely to change into something else. So a fairly notable example of this might be something like trying to reduce some unpleasant habits that we might have had as children. So for example, things like picking our nose and eating it as a child might not have been reinforced, and it might have been punished in certain ways. So in these cases, those kinds of behaviors operate on a lose-shift mechanic. We're being punished or receiving negative feedback for that kind of behavior, so we're less likely to eat what is up our nose in the future. We might want to think of a slightly more positive example where certain kinds of useful or pro-social or self-promoting behaviors are available to us, such as successful performance in any kind of education. So in these cases, we might operate, hopefully, on a win-stay mechanic. So this is the idea that if we receive praise or we receive high marks, and there are differences there between the internal and external motivation that we might receive for those things, then we're more likely to repeat and stay within a successful learning environment. So you can begin to see how these things like lose, shift, and win, stay operate not only in games, but also in the real world. So let's keep those things in mind as we look specifically to the game of rock, paper, scissors. Now, some of you will also know the game in other forms of description. It's also known as stone, paper, scissors, scissors, rock, paper, and the sort of social version of the game is called Rochambeau, and the bizarrely titled rock, paper, scissors, stone, which is something that I've never quite understood. Now, the history of rock, paper, scissors is also really, really interesting. It's an incredibly old game, and there are lots of different cultural versions of this game that have been around for centuries. So instead of playing rock, paper, scissors, what you might want to play is a Kitsune Ken game. And this has similar relationships between the rock and the paper and the scissors, but these are now expressed by the interactions between hunters, villagers, and foxes. Similarly, there is a Mushy Ken version of the game where you look at the interactions between slugs, frogs, and snakes. Now, this reference to the animal kingdom is actually quite apt. So in addition to rock, paper, scissors being a kind of fun playground activity or a good way to resolve a stalemate, the idea of rock, paper, scissors and the idea of this transitive non-dominance between items, and by that we mean that rock never always wins, paper never always wins, or scissors never always wins, can also be found in the animal kingdom itself. So these are three subspecies of lizards, and these lizards can be identified by the sort of the colouring that they have on their chin. There's a yellow, a blue, and an orange subspecies of this lizard. And individuals who've studied these lizards for generations have found this idea of cyclical dominance, this non-transitive dominance of individual species. So it's never the case that one species is better than any of the other two. It's always the case that the yellow is slightly better than blue, but the orange is slightly better than the yellow, and so on and so on. So if you look at the dominance of these lizards over generations, what you see is that you see the yellow subspecies enjoys a period of dominance, as does the blue, as does the orange. So this is exactly like rock, paper, scissors, in the respect that there's never going to be one particular item that's going to guarantee success. So as we play rock, paper, scissors, so too do certain subspecies of lizards. So at the risk of patronizing you all just for 1 second, what I will do is we will just clarify the rules of the game. So if we imagine ourselves in the white glove and our opponent in the blue glove, we have to simultaneously select one of three options. And we know that if we both pick the same option, then that's going to result in a draw. Then there's another third of the possible combinations that are going to result in a win, and a final third of the combinations that are going to result in a loss. So hopefully now we're all up to speed with the rules of rock, paper, scissors. So with that in mind, let's take a quick poll. Imagine for one bizarre, incredible moment that I might consider myself an expert in rock, paper, scissors. And given all this information that I've just given you about the game, what would you pick as your first response if we were to play together right now? I've already selected my response. It's on the next slide, so there's no smoke and mirrors here. But given everything that we know about the game, what would you pick as your first response against me? Very, very interesting. All right, well, I will put you, so the slight majority of people picked paper, and roughly about 25 or the rest picked a combination of rock and scissors. Thank you for the host for sharing that poll. I would have gone with rock. I always do the Bart bias, and there's a reason for that. So let's just reflect on what we're doing there. So for roughly about a third of you, you'll be feeling pretty smug right now. So this is a so-called expert in rock, paper, scissors, and I've just beaten them. For another third of you, you might think, oh, wow, this individual is like quite impressive. He actually beat me. And for another third of you, you might think we might have some simpatico developing because we both selected the same thing. Okay. Well, the second poll is what would happen if we played again? So again, think about all those things that we've just talked about. Think about what your response was. Think about what my response was. Think about how I'm thinking about your last response. Think about how you're thinking about your last response. And let's play again. All right, so now we're approaching a third. Again, I'll put you out of your misery. I just picked rock the whole time. I hate playing the game now because I study it, so I just pick rock every time. So anyway, but for all of you, you will have had a very unique experience in the kinds of things that you were thinking about. Maybe you thought I was trying to bluff you. Maybe you thought that you were thinking too hard about what I would do, so you were trying to change your response in response to that. Maybe you were thinking more myopically about your own response. There are lots of different ways to go here. So what we'll do is we're just going to take a look at some data that suggest on average what people tend to do in the game. And one thing that's really useful for us from a sort of scientific or psychological point of view is that when individuals play the game, we test performance often against this gold standard of performance. So often when we play games, we think about games in terms of two things. We're seeking to maximize our wins, and we're also seeking to minimize our losses. Now, when we play different kinds of individuals or different kinds of opponents, often we don't know how successful we're going to be. As a result, the only way that you can minimize your losses is by playing in the following way that's on screen. This is the only guaranteed way in the game that you're going to avoid being beaten. And that's essentially to play randomly. Now, we're not going to talk right at the moment about cases in which you can exploit opponents, but this is an opportunity for us all to minimize our losses, just be as random as possible. And what's really interesting from a sort of cognitive psychology point of view is that people just find it very, very hard to behave or think randomly, such that biases appear in the game that kind of betray our own sense of randomness. So we use this kind of metric, this 33 1/3, or this 1/3%, this 1/3 proportion, in order to test the degree to which people are being random. So let's have a look at some data. So this is data taken across a number of different studies in a number of different contexts and cultures. And what it seems to reveal, I should state that this isn't always the case, but a trend within the data seems to be that there is always this slight overplay of rock. In other words, it's the BART bias. So given this information that I'm secretly sharing with you all right now, we can start to develop some techniques in terms of potentially maximizing your wins. So we know if people deviate from randomness, and we know that people are more likely to pick rock, then what we can do as our first round is tend to pick paper. And this is exactly what the majority of you did at round 1. So that's going to be frustrating for our opponent in that we beat them more often than not. So we then ask ourselves, well, how can we increase our chances of winning at round 2? What's our opponent going to do next? Well, to do this, we think back to those operant conditioning or those reinforcement learning principles that we talked about right at the start. If you win, you're more likely to stay. If you lose, you're more likely to shift. Now, the game itself is slightly complicated because there's only one way to stay, but 2 opportunities to shift, and people talk about those different shift behaviors in different ways, but the chances are that our opponent is going to shift. And if we know that our opponent is going to shift, we can then adjust our strategy in order to maximize our wins on round 2 itself. But there's a problem here. The problem is these aren't going to be foolproof ways to play the game, and this is the reason why. So I just told you that there's a rock bias currently in the literature in most cases. So by telling you this, and as expressed in round 1, there's already, if people think about the game a little harder, there's going to eventually be, maybe 6 months, a year, 2 years down the line, there's going to be a paper bias. And if I've told you that there is a lose shift bias within the game as a result of these operant conditioning or reinforcement learning things that we like to do, then eventually, when we play the game, there's going to be a lose stay bias. So the strategies that we look at rock, paper, scissors are going to be cyclical. There's this transitive non-dominance about the items that we pick and about the strategies that we choose following outcome. And then in exactly these respects, we're exactly like the lizards who interact with one another across generations. So there's never one strategy that's going to settle down in this game, just like the lizards continue to challenge and compete against themselves in their specific domains. So this would be wrapping up essentially a discussion of rock, paper, scissors. But what I want to do is I want to spend some time to emphasize why we would be interested in this game in a broader context. Now, sometimes, because sometimes I do research into rock, paper, scissors, that would seem like a sort of an intuitively appealing thing for a newspaper to pick up on or something like this. And what's happened is that I've often fallen foul of the way in which the newspapers have reported the research. And the newspapers focus on the research in terms of rock, paper, scissors, not in terms of why we use rock, paper, scissors to inform our understanding about human decision making. So something that is no good for your self-esteem or your ego is to scroll through some comments in the section of newspapers. I will happily share some of these with you in my own form of negative feedback. So a comment from somebody in Liverpool, England. I wonder how much this has cost the taxpayer for the experts, that's capital E for experts, to come up with this. Please get a life. Someone actually dug a little deeper, which was quite impressive, and they said, well, from Denver. So, well, thank goodness it was the Canadian taxpayers who paid for this piece of tripe. So I would like to acknowledge the contributions of the Ontario Ministry of Research and Innovation for that, and that got 23 upvotes. Someone from London in the UK actually made an entirely reasonable comment. The comment here was that some of the data was based on 31 people, so it must be true. Okay, so this brings up a really important point about, is the data that we talk about in science reproducible? Can it be replicated across different samples and across different cultures and populations? And that's why I was keen to show you this graph. So we show that across studies that we carry out in our own laboratory, as well as laboratories across the world, that in a lot of cases there is a ROC bias. So this idea that we should be cautious about talking about data if it doesn't scale to other kinds of populations is a really important issue. So I thank actually that anonymous commenter for that idea. The final comment is from the Planet Earth UK, which is a very odd way to frame your geography, I think. But the comment is, well, they should be spending money researching cure for diseases like cancer or HIV. This is a stupid waste of time and money. So what I would like to do, and I think it's incumbent upon me to do so, is really just emphasize why we use this game to think about human decision making. So we'll try and summarize the kinds of things that we've talked about in this following graph. So again, what we're doing here is we're thinking about this kind of 33.1% as some form of gold standard into optimal play. So if you have no idea about the game, if you're unsure about beating your opponent, what's the one way that you can protect yourself? The one way you can protect yourself is by behaving in an unexploitable manner. And by an unexploitable manner, all I mean is that you're going to be playing randomly. There's no contingency between what just happened on the last trial and what's going to happen on the next trial. So it's really interesting from our point of view that a lot of the data that we see in these zero-sum games, when individuals experience a win, the distribution of their responses on the next game approximates this kind of rough 33 1/3 distribution. They stay 33% of the time and they switch into the other two responses, again, 33% of the time. So in these regards, we think about this data in the following way. We think about it in terms of positive feedback, providing you with a cognitive state that allows you to perform optimally. So being reinforced for behavior allows you to kind of just keep your cool, maintain some good quality, rational decision making. And the interesting thing from our perspective is that that's not the case when people are provided with negative feedback. When you're provided with negative feedback, you can see that the lose shift mechanic really comes into play. So the amount with which people stay is reduced and the amount with which people shift is increased. And you can see that if you're in a competitive environment, this is going to put you at a disadvantage and potentially make you exploitable. So we think about the data in this way. The receipt of a negative outcome puts you in a cognitive state that is less likely to lead to optimal performance. So the very receipt of winning or losing, experiencing success or failure, is going to put you into very different cognitive states that's going to impact your decision making for the future. Now this is really important, and it's really important for the following reason. So you can think about any domain within life. We're always going to have to fail before we succeed. It's very, very unusual that we would have a natural aptitude for anything. So Samuel Beckett emphasizes, ever tried, ever failed, no matter. Try again, fail better. We have to fail again, inevitably, but we have to make sure that we recover from failure in a reasonable way. So you might want to think about making a meringue for the first time and it being an absolute disaster. Or we might even want to think about learning a skill like tennis. We have to fail before we succeed. And this is where some of our data is leading us right now. What we're interested in whether expertise in these particular domains is defined by the ability to continually succeed or the ability to recover from failure. And to address these questions, we went outside of the lab and looked at some data that's out there in the real world regarding professional tennis. And for this, we created something that we colloquially called the Murray Matrix. So we can think about ideas of winning and losing and the effects of winning and losing on subsequent performance in professional tennis in the following way. So tennis is a really complicated game, and the experience of loss or win on any given point might be not attributable to yourself. What I mean by that is that someone just might score an ace. So there's nothing that you could have done. You lost, but you weren't necessarily responsible for that loss. So this is something that's important to us from a psychological point of view, is to identify when wins and losses were our own responsibility. But there is a subset of decisions that are made in tennis wherein successes and failures are your responsibility, and these are line challenges. So when a tennis player makes a line challenge, that line challenge can either be successful or unsuccessful. So what we can do is we can trawl through large-scale databases of professional tennis data to see the following. We can look at whether individual tennis players who made a successful or unsuccessful line challenge at point N then went on to win the point within that game on the very next round. So does the outcome of the line challenge at point N determine the outcome of the next point within that game? And what we seem to find in that data is that there are some contingencies between repeatedly winning and repeatedly losing. But the key here is what we want to do is we want to look at the role of expertise. So I'm just going to show you a few scatter plots that try to address this question. So this is the first scatter plot. What we've got along the bottom, which is also called the x-axis, is a weighted seed ranking. So as the number increases for this weighted seed ranking, we would describe this player as being relatively bad or relatively worse by seed. And I should stress that even though we might call all these players better or worse, this is very much a relative term. All these individuals would beat you hands down in tennis and probably a lot of other domains associated with physical activity as well. So 0 is high seed, 100 is low seed. And what we've also got on the running top to bottom or on the y-axis is the probability that the player will lose following a loss of an incorrect line challenge. And what we see is we see something that we would describe as a positive correlation between the two. That is to say, the worse the player is at professional tennis, the more likely they are to lose the next point if they've unsuccessfully challenged a line call on the previous point. So this suggests that recovery from failure is quite difficult. And what we can do is we can compare that with a scatter plot that again looks at the weighted seed ranking, but looks at it in the context of a repeated win following a successful line call. And that pattern is not true of successive wins. So this data seems to suggest to us that a hallmark of expertise is not necessarily the ability to repeatedly win, but the ability to recover from failure in a quick, reliable way. That seems to be the hallmark of expertise. So when we think about these cycles of performance, and when we think about what happens to us when we lose, and what happens to us when we win, we can think about extending the data that we've shown in these environments to things like gambling and education. So if we think about a gambling context, in a lot of gambling contexts, you might be interacting with a so-called opponent who is also playing randomly. There's no way in which you can maximize your wins against a slot machine, although many people think that they can. What we've shown in the data is that experiencing a loss, in this case the loss of money, might place you in a more exploitable position from a cognitive point of view. You might be more likely to play again, you might be more likely to enter into cycles of behavior that are going to make you lose more money. And in the case where in a gambling environment where you can be exploited, this increases the risk of exploitation for you. So the data that we collect in zero-sum games offers some insights into gambling. We also think about this data in the context of education. So let's imagine a case where we're filling out a multiple choice question. And on the quiz, for question 4, we think the answer is D. But we're really not sure that that is the correct answer. In fact, we're pretty sure that it's the wrong answer. Well, on the basis of a lose shift mechanic, what is that going to do for the individual completing this quiz? What that's going to do, potentially, is that when that individual comes to answer the next question, if they're operating according to a lose shift mechanic, now remember that they don't actually know that they've lost, but they have a feeling that they might be getting the answer wrong. They might be less likely to put D for the answer for question 5, because if they've lost, they don't want to repeat their D response that they chose for 4. So these kinds of thoughts that we have, these kinds of thoughts about our own thinking or metacognition might also be really important in the context of any kind of educational assessment. So again, thinking about zero-sum games and applying these operant conditioning or these reinforcement learning rules, such as win, stay, or lose shift, have other applications in gambling and also education. So what I'd just like to do to finish is I'd like to thank all the members of the lab who will be meeting with remotely shortly. This was us in somewhat different physically proximal times, and I'm really missing the popcorn and the cookies. And I would also like to thank again the Ontario Ministry of Research and Innovation, the Discovery Grant Programme at NSERC, and also locally Alberta Gambling Research Institute for providing funding that allows us to do this. My contact information is there if you want to follow up on any leads, but we'll have the chance to do so already. Again, what I'd like to do is I'd like to thank the university and the Faculty of Science for hosting, and I'd like to thank you all for your time, for your participation today. So thanks a lot.
Wonderful. Boy, so I have so many questions, and that's so interesting. And I actually, I'm going to ask the first question, Ben, if that's okay.
I guess that's all right.
And that is whether or not, so one of the things that people will argue about is whether it's a good thing, you know, when children are either in school or playing sports, whether it's a good thing to praise them sort of independent of their performance, and this kind of like trophy culture in youth sports. So even if they like were really bad soccer players or something, everybody still gets a trophy, right? And that was sort of the thing. I wasn't thinking about this in terms of kind of a gambling context or decision making, but in terms of encouraging success in our developing children. So does this intersect with that at all? And in terms of sort of making sure that the way that we treat our children in the system, no matter what system that is setting them out for better outcomes. Can you talk to that just a little bit? Or it might be unrelated.
No, I think it is related, and probably doesn't stop at sort of child development level either. So we have some data that might speak to that, and I can just very, very quickly talk about what we did. So what we did is we, again, we were sort of playing games in this context, but we were also asking people how well they thought they were doing. So what we wanted to look at was this sort of discrepancy that you've sort of alluded to, is that, you know, how well I actually did versus how well I thought I was doing at the time. And what we look at there is we look at the degree to which people operate optimistically or pessimistically. And the data seem to suggest that potentially thinking optimistically might have some similar effects to actually being in an environment where you are successful, if that makes sense. So we've sort of suggesting this idea that the cognitive state that you're put in when you directly experience a positive outcome is going to be good for you. You're more likely to conduct more rational, more thoughtful, optimal decisions in the future. One thing that we're talking about in the lab is that if you can't establish objectively that success, it might be that optimism helps to kind of reframe or support or give the illusion, at least, of success. So optimism might also help you, put you in that cognitive state that makes you more rational, more thoughtful, and less likely to be impulsive. So there's going to be a case where that bottoms out, you know, so that's where we have delusions, I think, in terms of, yeah, it's like, you know, I decided that I'm never going to be a professional drummer. I know that now, right? It's never going to happen. So there's no amount of optimism that's going to help me perform better in that particular context. But it might be that optimism plays the same role as actually experiencing wins to some degree.
Fascinating. So I'm looking at some of the other questions here. Some of them I think are going to be answered, and it looks like we have some coming in. So here is a question. First of all, it's thank you for a great talk from one of our listeners. And her question is, have you studied simple games involving more than 3 choices? And how does having more choices affect decision making?
Right, so yeah, so one thing that we're thinking about this, so I should say that there's actually a simpler version of rock, paper, scissors, or at least a game where there are only 2 responses, and this is called matching pennies. And it's an easy game to source, but essentially you or your opponent is picking a heads or a tails, and you decide on the rule that if you match, you win, if you mismatch, you lose, or something like that. So the degree to which you have different responses available to you might influence the degree to which you shift. So it might make sense from the rock, paper, scissors point of view, and as I mentioned in the talk, there's only one way in which you can stay, but there's multiple options for shifting. So this might just make you more likely to shift just because there are more options available, right? It's like if you choose to shift your behavior, there's a multitude of different things that you could do rather than the thing that you just did. So you might be also interested to learn that there is a 5-response version of rock, paper, scissors, and there's also a really neat 3-response game that people might want to do some further research into, called the Monty Hall problem. And I won't say anything more about the problem. It's good to go in sort of naive and think about what your own responses would be. But when we think about shifting behavior, or at least the decision about whether to stay or shift, the Monty Hall problem identifies that there is an emotional component to that, and the emotional component of remorse. So say, for example, that I shifted my behavior, but it turns out that if I just stayed with my original thought, I would have won. And again, people sort of think about those kinds of potential outcomes. They mentally simulate those outcomes such that the potential for experiencing remorse, if only I'd have stayed with my original choice, that can also influence decision making. So that might have an impact the more shift behaviors you might engage with. So if people want to go further with that, there's matching pennies. There's an elemental rock, paper, scissors game that involves 5 responses. And there's also something called the Monty Hall problem, which makes you really think hard about the remorse that you might feel if only you'd have stayed with your original choice.
Fascinating. So we have a couple of questions about investment strategies and both from the perspective of how is this applied to investment decisions, but also from the perspective of industry and the investment industry and how that might be, I don't really want to say exploited, but I guess how does this decision making and the properties that you're learning about decision making influence both how people make investments and how the industry is framed and set up?
Okay. So my disclaimer is that I am not the person to talk to about investments. Anyone who knows me will attest to that. There is a whole other, I mean, the one great thing about these zero-sum games is that it's approached from lots of different perspectives. So you can read psychological perspectives, non-linear dynamics perspectives, and also economics. So economics, the economics faculty uses these kinds of games also in trying to address exactly these kinds of questions in terms of understanding how people invest. The one thing that comes to mind in terms of investments, or the one thing that comes most immediately to mind, is this idea that there might be evidence for lose-stay mechanics in investments, this idea of sunk costs. So the worse an investment is going, or the more money you might be losing on an investment, again, there is an investment in multiple senses of the word, and this kind of idea of remorse, right? So if I sell it and then it goes back up, I'm going to feel really, really remorseful or really, really regretful. So you can think about lose shift or even lose stay mechanics or win stay win shift mechanics in the context of investments in economics. And what's kind of interesting from an economic point of view, similar to the observations that we have in psychology, is that even when people are playing with their own finances, there are biases and people don't operate optimally. There are often these sort of what we might describe as irrational biases or impulses that don't make us make the optimal decisions. So just as we might understand losing as rock, paper, scissors is a negative outcome which impacts on the next round, like an investment portfolio that's continually losing money, there might also be biases or metacognitions or even emotions that influence the degree to which you're going to keep or sell that particular stock.
Interesting. So there's two questions that I want to get to, and I'm being mindful of the time for everyone, but this is an important question. Has rock, paper, scissors ever been used by world leaders or politicians, to your knowledge, to make decisions where there is otherwise an impasse?
So the example that comes to mind was a controversial example where it was I think it might have been a soccer game. This is my first example where the referee forgot to bring their coin. So they played rock, paper, scissors, and then I think there was some challenge against the game being null and void or something because this wasn't an accurate way of deciding who would kick off. In terms of using the game as an impasse, it kind of sounds scary, but I guess random, right? The connection with something like war or politics is quite apt. So unfortunately, I'm blanking on the particular conflict, but there is a literature that discusses or looks at certain moments in conflict or war as examples of zero-sum games. or as examples of something like the prisoner's dilemma. So that might be another thing that the participants, if they're interested, could follow up on. It's another example of the game where it's a potentially collaborative or competitive game where you have to figure out what your other prisoner is going to do. But if you both do one of the options, it's good. But if you both do the other option, it's really, really bad. And there's been some historic reviews of certain political conflicts that have been described in exactly these contexts. So the link between things like zero-sum games and things like war and politics is very, very apt. I can't think of a specific example where things have been resolved by rock, paper, scissors, but you always play rock anyway. So,
So I think this is going to be a tough question, but one that I think several of the listeners will be interested in, and that is, do we understand sort of from a neuroscience perspective or a mechanistic perspective, why people tend to downgrade when they lose? I mean, do we understand mechanistically or physiologically why that happens?
Yeah, so I think that there's an interaction there between maybe two literatures at least. There's a maybe evolutionary perspective, and also there's a neurological perspective. So I'll speak just briefly to the evolutionary point of view. And also economics actually. So so the argument has been, or the argument seems to be, that the consequences of staying following a win are less dramatic than the, sorry, I'll start again. The consequences of not staying following a win are less dramatic than the consequences of not shifting following a loss or the threat of loss. So there's some really wonderful quotes in the literature, like, you know, the gazelle cannot afford to lose, or you cannot calculate trajectories while being chased by a bear. So what this does is this kind of emphasizes the idea that the consequences associated with losing again are much more dramatic than the consequences associated with winning. And this might be why lose shift is seemingly a much more reliable mechanism than win stay. You know, if we don't run away, or we don't change our behavior while being chased by a bear, we're not going to be running anymore. That's kind of like the evolutionary perspective. And this ties in with an economic perspective known as not universally accepted, but this idea of loss aversion. So the subjective value or the subjective experience of loss is much more dramatic than the subjective experience of winning, even if the objective value of those wins and losses is identical. So we much greater store in loss than we would in win. And there's a nice phrase where losses loom large. So, you know, we win 10 bucks or we lose 10 bucks, the loss of that 10 bucks, we're going to feel much more. And tied into that is also a neurological perspective. So we also in the lab we also record electrophysiology. So what this means is that we can record in real time the electrical fields generated by the brain by putting electrodes on the scalp. And the one thing this provides us with is this really elegant millisecond accuracy about what the electrical fields are doing in the brain when people know that they're losing or winning. One of the components that we specifically look at is this thing called feedback-related negativity. So what this is it's an electrical field generated by the brain, and it comes online about 200 or 300 milliseconds, not seconds, milliseconds, after the individual has experienced a win or a loss. And we think this, the literature thinks that this is associated with the release of dopamine, specifically in relation to a part of the brain called the the anterior cingulate cortex. So it's the changes in dopamine levels at the ACC, and that's reflected on the scalp by looking at this thing called feedback-related negativity. So what's super cool about doing this electrophysiology work is that the kind of brain knows before you do whether you've won or you've lost. So what we do is we look at the size of this feedback-related negativity according to whether people are receiving wins or losses, draws, high wins, low losses of different values. So we look here to see how the brain is automatically categorizing different kinds of outcomes. So for example, is a draw treated more like a win or more like a loss? And that gives us some indication about whether people are being optimistic or pessimistic again. If you think a loss is a near miss, it's like, well, I was pretty close, maybe next time. Or if you think a win was a near loss, you think about draws in different ways. And what you can do is you can look at the brain non-invasively, which is related to the way in which individuals categorize outcomes. And what seems to be the case, tying back, sorry, this is a very long answer, tying back to the evolutionary and the economic arguments, is that the response to losses seems to be much more robust, much more inflexible, much less flexible, I should say, than the response to wins. The brain state seems to be a bit more flexible following the receipt of a positive outcome relative to a negative outcome. And that's really interesting because it ties back to this idea that shifting following loss is a bias that is much harder to get around.
Fascinating. Well, thank you so much. It was really interesting. And there are a couple of questions that we didn't get to, but that are being answered. And one of the questions is whether this recording is going to be available. And actually, all of our Science Connect webinars are available to everyone interested in this science. So thank you so much, Ben. Thank you to all of you for joining us. We'll look forward to our next Science Connects webinar on August 13th. And during that seminar, Associate Professor Joshua Evans will be sharing research on the Affordable Housing Solutions Lab, which is dedicated to the co-creation of innovative and affordable housing solutions that are important for Edmonton, important for Alberta, and beyond. Watch for the post-webinar email that will be coming out. There will be more information on how we can connect with one another, opportunities and ways that you can support initiatives in the psychology department, and lots of ways for you to share your feedback. So with that, thank you so much, Ben, for sharing your science with us today. And to everybody joining us, please take care of yourselves and stay in touch. Bye-bye.